the definition, think a little bit harder. You know? So we've got this definition of j star of x, which is the minimum of this integral. You know, there's we're going to minimize over all functions of time, say all continuous functions of time, and assuming the minimum exists. And you know, u of t generates x of t because we have a differential equation. You know, of course, there's an initial condition. And that's what I mean by j star of x, because that's the initial condition. All right, you all with me? And so we want to use the same insight we used before to get this converse theorem for Lyapunov functions. And so we're going to, you know, write this in two parts. But we got to be a little more careful here. We have to think a little harder. So again, we're trying to, you know, let's pretend we know x star of t. Okay, let's pretend we know everything. We're just trying to derive properties of j star. So if you know what the optimal solution is, you know, for any input u, I can say, well, I know I'm going to end up somewhere here. I'm going to be, let's denote, you know, I'll have to write it down. Okay, so I started with x, I travel along. You know, somebody gave me a u of t that was crap, okay, but I'm just putting it in to play with. And I go along, and I go here, and I know that wasn't the right thing to do. I know what the optimal solution is. You should have done, I wish I had another colored chalk, you should have gone this way. You know, this would be optimal starting at xm. You see how it's going down? You know, that's cheap, okay? And it's not going down. So basically what I'm saying is that rather than keep going with this dumb u that you gave me, I could instead, all right, I'll take that stupid u you gave me up till now, but from now on I'm going to take what I know is the optimal policy and go on forever, okay? And what will this integral be if you do that? He said it? Anybody else want to say it? Because this is what I'm testing to see you understood before, the fundamental theorem of calculus before. The step in that, before I said, oh, well, this is just j of xm, you know. But now it's not. This is some horrible big function because I chose a stupid u if I choose this one. But if I modify for the optimal x star at that point, then this will be j star of xm. So to summarize, j star of x is equal to the minimum over functions u of this integral but plus, forget that, I know that that should be j star of xm. And you see here that before I got rid of the brackets, because before I had u as all trajectories from 0 to infinity. Now this is only an optimization over trajectories on a finite window. So it's u's on the time horizon 0 up to tm. And just like before, I'm going to let tm go to 0. So I'm looking at only u on a tiny interval. All right? And that's called the principle of optimality. And if there was a Russian in here, I'd be yelled at, because I'm sure that there's Russians who claim to have done this before Bellman, and maybe they did, you know. But Bellman was an amazing scholar and did beautiful, beautiful work, concurrently with a lot of brilliant Russians. So there was an arms war going on in control theory at the time. and we won because we got a lot of the best mathematicians to move from Yugoslavia and Russia to the United States. And it's really true. I mean, Pontryagin, who did some of the most amazing, beautiful work, was one of our people we were able to recruit, and a lot of brilliant people. And for some reason, Yugoslavia was the gold mine of people in the area. Yeah.
So, what exactly is the principle of optimality? It's Thank you. I mean, usually, this is the only time I've ever forgotten to say it. It's that. That's right. I'm kind of lost for words for a second. Seems like
it's just the fact. It's sort of a memoryless property that if I've gone through and I'm all good, I'm all good, and I say, well, now what do? I can just forget the past, pretend this is the initial time, and then optimize, solve my optimal control problem as if the past didn't exist. It's really just that. The fact that I look at my current state, forget about the past, and I optimize forward. And that's what that is. Yeah. Yeah, it is. Yeah, it's really the memoryless business. But yeah.
I mean, doesn't it also kind of apply, like, if you happen to be at the optimal position, like, it doesn't matter what the past is. I mean, like you can take the optimal trajectory and divide it up into segments, and each individual segment's going to be optimal between those 2 points.
Yeah, that's true too. That's hard to work with, but absolutely true. Yeah, this is really useful in terms of algorithms and things like that. But what you said is correct as well. That oh, wait a second. No, hold on a second. But be careful with that. We have to know what we mean. Now, it's part of an optimal solution, right? I mean, it's really critical they integrate from 0 to, from this intermediate point to infinity, to say that is optimal. I mean, you're right that, you're right. It's, if I integrated to another intermediate point, it'd be a piece of an optimal, I don't know, it's hard to say it again. Maybe I misunderstood your point, I realize.
I don't know, I'm just trying to think, you're trying to get from A to B in like an optimal path.
Yeah.
And it seems like even if you like trying to get to A to B, and you take a certain path, I don't know, like divide, like little segments of that are still optimal from those little,
Yeah, but defining that's hard, you know what I mean? Defining the segment being optimal. It's really easy to say that this trajectory is optimal, starting at at the intermediate point. That's really precise. But it's harder to say what a segment being optimal means.
In this formulation, your beam point might change depending on your starting point. So like if you do a suboptimal U for some time, and then you do the optimal U after that, your endpoint might be different than had you done the optimal U the entire time.
Well, that's what's being modeled right there. If I have a suboptimal U, I'll be at the wrong X. And that's what's being, So you've got this myopic cost here, and that's called the cost to go. I should have said that too. So you've got something very myopic, and then something that takes into account the future. So they're both being modeled there. And so you had a point too.
Yeah. So I can there's what appears to be a recursive nature in this formula right here. It seems to be solved backwards in time. Or?
Yeah. I mean, that's another point. Yeah, we'll get back to that. This is not. This is not. So I mean, I think I can kill this now, right? Yeah.
Just think here we are integrating up to infinity, right? The time is infinity. Like what if we know the final time or something?
Yeah, right. I mean, a lot of things change. Yeah, I wasn't going to talk about this, but if instead of integrating to infinity, you integrate to a finite time, things aren't as pretty because J will depend on, I mean, God, I mean, you end up having to take into account the time horizon as well. That's really ugly. Oh yeah, the principle of optimality is so universal, it's ridiculous. You know, for finite time horizon problems, anything. I mean, just you know, traveling salesman type problems, anything. it's so universal. It's crazy. Almost any objective function. And we'll see it very trivially for Markov models, and we'll get recursions that we can solve to get numerical methods. And there is a backwards in time business, but that's we'll come back to that. Maybe not today. Okay. Yeah. Yeah, we're good. All right, but this can go, right? So we did this, and we got this principle of optimality, and now it's kind of obvious what to do, right? I mean. It's a little bit harder to get your head around, you know. But let's just rewrite this one more time. You know, we have 0 equals the minimum over U on some interval 0 to Tm, and Tm is 1 over the number of atoms in the universe. Okay, it's 10 to the minus 10 to the 10 to the 10 to the 10 to the 10 to the, I don't know. So think of Tm as so tiny it's ridiculous. Okay. Is it all in your heads? Really small interval. What I do here, I took the J star of x and I subtracted. So subtraction was not in the handout, but you're all supposed to know what that means. And then I divided by both sides by Tm, and I got that. So nothing more than what I did before with the converse theorem for Lyapunov functions, right? And now it's a little tricky, you know, because you have to know something about the process. You have to know that U is continuous. Let's assume it. All right. So if U is continuous, all right, and I'm saying that T is so small, it's basically, I can assume U is constant here. And then you get the HDB equation. And remember what the derivative of this is? It's the differential generator. Same technicality as before. I don't know this is smooth. You know, I don't know this is continuously differentiable. So I can't use the chain rule. So all I can say is that the derivative of j of x of t with respect to time, evaluate t equals 0, you know, I can only look at that, you know, but this is the HDB equation. And if you know, if J star is continuously differentiable, this is true. Okay, C1, continuously differentiable. That's what it means. And there it is. See, so I mean, I beat, you know, half an hour. It's really nothing, you know. So again, verifying that would be hard. You know, that would take a whole course. Yeah.
What's HJB?
What's that? Oh, Hamilton-Jacobi-Bellman. Yeah, Hamilton-Jacobi-Bellman equation. Yeah. And there you have it.
Essentially, what you do in this step is you take that cost function outside the integral.
No, I didn't. I said that basically, again, Tm is really, really small, and these guys are continuous, so they just don't change. I'm moving this Tm, so I'm right there. So x of t doesn't change. I mean, I can't, if I could zoom in the number of atoms in the universe out, you'd see that it's just constant.
So I guess I'm not really too math.
So
sure.
This is x of 0.
So it's like, I mean, you're integrating from 0 to 0, essentially, which is 0, then 1 divided by 0 is infinity.
No, just think of it as being constant. So x of t is constant.
Okay.
Because on a very, very small window, it doesn't change much. So this is constant, that's constant. You integrate a constant, you just get Tm times a constant. You divide by Tm, you get constant. And there it is.
Oh yeah, that's what I meant. You assume that cost function, that C is constant.
Yeah, it's basically constant over that interval, assuming continuity of U. If U was crazy, then we'd have a problem, but it's not going to be under. Yeah.
The only thing with the subscript U for du with the differential generator, it's just because it's a control.
Yeah, that's right. So it's exactly the same definition, but I had f of xu instead of f of x, if you look back.
All right. U is completely defined within that operator, though.
No, I mean, U is I mean, we have a first order, we have a derivative of U here. I mean,
because like in the line above, that part of the solution is not a function.
Yeah. So what that x is. So this was a minimization over functions, but if the interval is small enough, it could approximate by a minimum over constants, because U's not going to change much on a tiny interval. That's all. That's all.
But well, because I was going to ask this question, was there a reason that you're putting the brackets around the minimum? Because the J star term is not a function of U. No,
du. Oh, let's write this down again. Yeah. So this is the way you would see the HDB equation in any stochastic control course. In a deterministic course, you would see this is the HDB equation. Let's write it down again. Okay, and I held off writing this way because I don't know that this thing exists. So let's assume it exists. So J star is continuously differentiable. Assume J star is C1, then I can do this. But the fact that this is a definition of a derivative, I mean, right there, I let Tm go to 0. That's the derivative of J star of x of t with respect to time. So getting the derivative notion right is really easy. Once you have to actually get it, use the chain rule, makes it a bit harder. And that's where you have to verify that smoothness property. Okay, but so there's a U right there. Okay, and so that was the myopic thinking. If I didn't have this term, that would be the greedy thing. Just given the state x, just find the cheapest state, the cheapest control. And then this is the thinking to the future. Right? And the minimizer, under conditions, well, the same reasoning. I'm saying, well, if Tm is so small, I might as well assume U is constant. I won't lose much. This was supposed to be, U was supposed to, the minimizer was U star, my optimal input. And so therefore, I get my state feedback policy. So I'm going to use stars for minimizers, but this minimizer depends on x, and I'll call that phi star of x. So this is just notation. All right. Under conditions, that's the optimal policy. And there it is. So this is all that most people will ever learn in optimal control. And then you take it for granted. You know, you're given a system like this. Then you go through and you look at this this differential equation, which is, you will see, I'll give you an example, I have time, and you solve it, and you get a state feedback policy, and then you say, is it reasonable? You know, and you then go through and you try to verify that it's optimal. You know, so rather than try to prove J is smooth and all this stuff, forget all that. You know, in practice, you would just go through and solve this, and then and see if it all makes sense, you know. And in the end, you'd find, oh God, yes, of course it makes sense, you know. And you can verify it's optimal after the fact. But that's, you know, yeah. Every problem has its own structure, really, that you'd exploit. But yeah.
What like aspects of this would change if you had like an explicit dependence on time of the dynamics? Does it just kind of carry through?
Yeah, it's ugly. If F depends on time, then a lot of this prettiness goes away, and we'd have another term with a derivative with respect to time here.
Okay.
You know, and then
you wouldn't necessarily have like a strict state feedback policy.
yeah, we get a time varying state feedback policy then. Yeah, yeah, it'd be time varying. And you could think of it. There is no such thing as time varying. Time is a state. T dot equals 1. You can actually get rid of it that way. It's true. You know, T dot equals 1, you're done. Yeah. So you can actually, this carries over to time varying case. Yeah. All right, T dot equals 1 is a perfectly good state space model. Yeah. So you really can instantly just drive all the theory. It's pretty nice. And if it's a finite time horizon problem, it's really unfortunately ugly. And then you've got to, if it was finite horizon, then J would depend on, we'd have something that depends on the time horizon as well. It would be.
So you're saying if we did have like explicit time dependence,
no, if we had
put time in the state with that?
No.
We could still work with that.
Well, so having time dependence in the dynamics, trivial, because I just say T is a state, and T dot equals 1.
It becomes part of the X vector, the same result here.
Yeah, that's right, because I just have the augmented state, and then the time will be right there. Because xt will... What? Oh, really? Oh, yeah. But when you have finite time horizon, it's sort of ugly. It's okay. I mean, the principle of optimality holds, everything holds. It's just the fact that when you talk about the cost to go, it's a short time horizon. And so you got to keep track of the dependency on T, you know, and again, you get a different differential equation, you know. So, but anyway, yeah.
So U star is a function of the initial state?
No, I mean, no, not at all.
Function of every state?
No, there it is. It's totally static. So the optimal input is a static function of the state. And oh, there's a star missing. Yeah, that's the optimal state. Yeah. And of course, I mean, you need conditions again. I mean, you know, I mean, what if this had 2 minima and you chatted back and forth? This wouldn't even be continuous, and you know, you need assumptions. You know. Yeah.
So the interpretation of the star on the X, wouldn't that be that if, say, for the first TM second you did, the wrong mu, and then you're at the wrong X, at that time the thing you should do is assume you're at the right X and do that?
No, this is all just analysis. I mean, having a bad U and then a good U was just a way to derive an equation.
Well, but
yeah.
I mean, this...
No, this has to be true for all T.
Okay.
Yeah, you can't screw up once. If you choose the wrong input for a microsecond, you're suboptimal forever. You never can make up for it. Yeah.
Yeah, I mean, and
that's where the team
star is just that, you get the X star, U star, like it's all part of the optimal. Even the state is optimal. For a specific optimal control input, the state will also be optimal. Right?
I don't understand. I'm just saying, yeah, there's a pair, an optimal input and an optimal state, and they're related just by a static relationship. That's all. Yeah, and you can't say anything more. And I wish I wish I could teach, the optimal control course, because the other way of looking at this, which is Pontryagin's minimum principle, is so beautiful, and it's a totally different way of thinking about things. In the lecture notes, I mentioned the Hamiltonian, but I don't talk about the beautiful mathematics behind it. I think maybe Jacob Hammer covers that in his course. But it's a totally different way of looking at things. It's, it's almost just worth telling you, just so you'll be interested. Just one comment, and I'll give you an example. Anybody here take convex optimization? Jonathan? I've got a minimization problem subject to constraints. I tack on a Lagrange multiplier. And it turns out that lambda t solves a differential equation. So lambda t is a Lagrange multiplier associated with this constraint. So you just consider this a constraint, just like in linear programming. It's so awesome. He must have the most exciting discovery that's actually worked. And so if you've taken a course in convex optimization, you can relax constraints using a Lagrange multiplier. And lambda t just denotes the Lagrange multiplier. And it turns out the Lagrange multiplier satisfies the differential equation. And you can solve everything. And I won't go through it, but that's a totally different viewpoint, and it's really powerful numerically. Because the problem with this is trying to find, on a large state space, trying to solve this for every x is really a nightmare. And when you look at this point of view, you're able to just look at one initial condition and just solve it for that initial condition, period. And that numerically can be much, much simpler. And also the math is insanely beautiful behind this. But the best reference is Leuenberger. He makes it seem like no harder than a finite-dimensional optimization problem. It's amazing how clean it is. But that's way outside the scope of the course. I just want to mention that's another point of view. All right, so just an example, and we'll quit. Yep. What?
Function is convex?
No. The thing is that if you have linear dynamics and C is convex, it becomes a convex program. But Lagrange multiplier theory goes outside of. It's still applicable in non-convex domains. So you still get necessary and sufficient conditions for optimality. And again, lambda solves the differential equation going backwards in time. That's really elegant. That's really cool. And it's very easy to derive. You can do this in 30 minutes as well. If you, again, just,
yeah. Things like, it may not be the minimal solution, but it will be a stationary.
Yeah, it gives you a stationary point. Yeah. That's right. This, here we use the fundamental theorem of calculus. Here you use integration by parts. It's the main step. The genius was to think, I'm going to relax this constraint. Holy shit! The nerve of doing that. really. But then once you do it, it just falls apart. And you apply integration by parts, you get a differential equation for lambda. It's really, really cool. Okay, but I think it's helpful to go through an example just to make this concrete. All right. And just make it a little bit harder than the standard example. How about That's pretty boring. So x dot equals u. I can just make the speed. It's one-dimensional. I can make the speed anything I want. Positive, you know. But I've got a big penalty for adjusting the speed. Oh no, it's not so big actually. I'm not so yeah, it's not so bad. A big penalty in the state. So the fourth moment of x, but only the second moment of u. So that means, yeah, so for a large state, you can imagine I'm going to hammer this system because my state cost is so big and my control cost is relatively so small. I'm going to say, that's going on? I'm going to make an enormous control effort. All right? Is that clear? Yeah.
Designing these cost functions is all just relative, right? Compared to each other.
Yeah, that's right.
So I mean, this wouldn't be any different from like x to the 8th to u to the 4th or something.
Oh no, it would change. You'll see that. Yeah, if you had x to the 8th and u to the 4th, you'd get a very different answer, which you'll be able to guess at the end of this. Yeah. Yeah. Okay. What's that?
X to the A, U to the D.
Yeah, I mean, you could work that all out for any A and B. Yeah, you could. And so, so we've got the minimum principle there. We can just write it down. You know, you've got a cost. Somebody gives you a cost function. That's f. You know, that's f of xu. It's just u. Write it down. 0 equals the minimum over u. C of xu is just u. I mean, sorry. X to the 4th plus u squared. F of xu is just u. And grad j star of x is a thing we don't know. So we pretended we knew it to get the HDB equations. Now we have an example. We have no idea what this is. But you could kind of guess. Does anybody have an idea how quickly it would grow? I've got a state cost with x to the 4th. And some of you have a lot of intuition about this. I know it. So do you think j is like x to the 4th? Because x is like x to the 4th?
Well, it's like the integral of it, right?
Yeah. Well, like the thing is, remember, u gets enormous when x gets enormous. In this case, you can guess really fast because there's such a, you know, it's so much more expensive to be in a big state than having a big control. So, you know, so u is going to be something, you know, maybe at least like a huge constant times x. Like minus 100x. Probably something even worse than that. You know. So if it were linear, if it's not. You know, you can solve this. You know, x of t is x of 0 times e to the minus kt. So if the optimal input was linear, then the state would be a linear function of the initial condition, and you'd plug this in, and you get a 4th power. You know, basically, you know. And so you'd get that j of x was something like some constant times x to the 4th. You know, I mean, just to get some intuition in advance. You know.
It's an integral, right? So it won't be x.
No, this is see, this goes to 0 exponentially fast. Yeah. You know, this is e to the minus kt, independent of the initial condition, multiply by that. You know, I square this, or raise it to the fourth power, I make this go to 0 even faster. Okay? Yeah. And this term here is trivial, you know, because the square compared to the fourth power. So that's what I'm saying. It's, you know, there'd be other terms, but the dominant term would be x to the fourth. Well, that turns out to be no way. It's not, that's too big. J star is much smaller than that, actually. And it's not consistent. I mean, if you tried to plug in this, something like x to the fourth into this equation, it wouldn't work. You know, I'll let you play with that. All right. Yeah, but it's a good idea when you get problems like this to play around and get intuition. So, you know, what if I chose a linear control? Would it, you know, something where I can easily compute the value function and see if there's any mismatch or anything. Yeah. But in this case, we don't need to. I mean, look at this. That's a function of x, and it's linear in u. U squared. We all know how to minimize that, right? Okay, just take the derivative, set it equal to 0. All right. Okay, so I mean it's one-dimensional. This is the derivative with respect to x. Okay, gradient just means derivative here. But so and that's evaluate u equals u star at the minimizer. Okay? And so I differentiate that. I get 2u. So we get our state feedback policy. We get that the optimizing u, I'll put the star in there, you know, the minimizer in this equation.
That should be u star, right?
Yeah, I mean, yeah, and by u star in this case, I just mean the solution to this equation. Okay, so I'm not talking about trajectories. I'm just looking at this static optimization problem. All right. So u is one, but more importantly, I forgot the gradient. There's a gradient there. Yeah, the derivative with respect to x. All right. So J is massively exploding because of the fourth power here. And so that's consistent with what my conjecture that u is going to get really big for large x. All right.
So we don't know what J star is.
Well, we still don't know. So we do now know that u is gradient descent, x is gradient descent. Which is sort of fun. So it's basically a steepest descent algorithm. This is always going to happen. You know, really, that's always the case. But yeah, we have to go through now. We know what u star is, and we plug it in here, and we got to solve it. We plug it in here, and we have to solve it. So I've got to square this monster here. There it is. So I get, you know, plugging in what the optimizing u is, I get there's u squared, and there's the dot product. And this is what always happens. You get this differential equation that's horribly nonlinear. You know, so this is 1/2 squared is a fourth. These two terms are the same, except for different scalings. I've got a -1/2 here, and I've got a 1/4 here. Isn't that lovely? So I get that I can go through, I've got 0, blah, blah, blah. I can multiply both sides by 4 and then take the square root. But be careful. So it's plus or minus, I'm taking square roots. Again, take the square roots. I don't have to go through this in detail, right? take this other side, take square roots of both sides, multiply by 4. I'll get twice x squared. All right. All right. And we all know what J star is then, right? I mean, it's some plus or minus 2/3 x cubed. But Jesus, J star was an integral, all right? J star was an integral of a cost which is non-negative. So we know that we don't need the plus or minus there. Okay, yeah. All right. You know, we know this is always positive. J star of x is positive. So it's x cubed. I said with a dumb linear controller, it would be like x to the 4th. It's actually, you know, 2/3 absolute value of x to the 3rd power. And we know what the gradient is. It's given by this formula, which was our optimal controller. There's a half there. So u is like x squared. Now we could plug this back into here. So u star t is equal to the half and the 2 cancel, and it's minus x star t squared. But it better be pointing in the right direction. If x is positive, I want to go towards the origin. If x is negative, I want to go towards the origin. So you have to put in here a sign of xt star. You know, so you're traveling in the right direction. If I'm positive, I want this to be negative, and if x is negative, I want it to be positive. And so this is one example. You can do everything by hand, and it's intuitively nice. You know, you get this incredibly large control action because of the mismatch in cost. And also, if you're small, if x is small, x to the 4th is really small, so you don't care so much. And that's also consistent, because if x is small, x squared is really small, so you give up. You don't apply much control effort. So it's that mismatch that causes that. All right, that's all crystal clear. So you've seen the whole theory of optimal control, the HDB equations, and this is like one of the only examples you can solve by hand. You know, besides the linear case, linear and quadratic. You know, everything's closed form expressions. You know, it's because it's one-dimensional, you know, and so I've got a square here. If this is two-dimensional, I couldn't take square roots, so I'd have to use numerical methods of some sort. All right, that's it. So you know everything you need to know about deterministic theory, and what we want to do now is develop the stochastic counterpart. So starting next on Monday, I'll be gently reviewing Markov chain theory, because 90% of you say you don't know what a Markov chain is. I don't believe you, but I'm going to review it anyway. And I've got you doing homework to sort of review all this as well in parallel. And so you can go back and go back to this handout. And I'll be covering this on Monday, the beginning of this, and looking at state transition diagrams and all of that. Okay. Meeting adjourned. Oh yeah. Oh, you had a question, or I don't know. Okay.